I don't know what your experience is, but we're now going to start quantum mechanics. And I don't even know how to begin this section. Because when I think about quantum mechanics, as I've been writing on my lecture notes, well, quantum mechanics is the deepest picture we have of reality at the atomic and subatomic level. And there's so much that goes through my mind when I think about it. It's like, it's really, I don't even know how to express myself. It's like really out there. And it's a very subtle theory. It's not like everyday tinkering of, physics, everyday physics. It's quite categorically different. And I was talking to some people in office hours, and I said, this is what I said to them. I said, quantum mechanics is a very non-human, very non-intuitive feeling that you get when you start to deal with quantum mechanics. It's like, at times I feel like we've contacted an alien mind. And I mean, or just like, how does a chicken think, right? When a chicken walks around, do you really think you know what a chicken is actually thinking? I don't. And when I think about quantum mechanics, I kind of think of that chicken because it's so foreign to me. It's so out there that it's like really beyond anything that we can imagine. Furthermore, when you look at the people who actually founded quantum mechanics, in some sense, they started to hate the topic. And, there's a lot of really, really good quotes from these people. And, Bohr, one of the founders of quantum mechanics, says that, when I think about quantum mechanics, I start actually getting dizzy at times because I keep shaking my head going, that's not possible. And so he's literally getting dizzy from all this back and forth head shaking, going like, this can't be true. This can't be true. The problem is that it's true. Okay. I would say it's the greatest achievement of the 20th century science. And the reason why it's greatest achievement, it's not because it's more important than, other discoveries like the theory of evolution or the Big Bang theory or anything like that, or some, the vaccine of some, something. It's not that it's better. It's more important because I think it's more, it's a bigger achievement because it defies all of common sense. But when you look at the discovery of the genetic code, it was very categorical. You go this way. It's very stepwise how you get to the genetic code. That's not true with quantum mechanics. It's so, there's one of my favorite quotes of all time is by definitely my idol, Richard Feynman. And Richard Feynman said something that summarizes it better than anything else I've ever seen. Okay, and let me share this with you so you could see what he wrote. But this is a direct quote by him. And I would say this is in my top 5 quotes of all time. And he goes, and he says something like this. There was a time in the newspapers said that only 12 men understood the theory of relativity. I don't believe that ever was such a time. There may have been a time when only one man did because he was the only guy that caught on before he wrote his paper. And what he's talking about, he's really talking about the general theory of relativity. Nobody really understood what was happening before Albert Einstein wrote about it. But once you read the general theory of relativity, it actually makes sense. You look at that thing and you go, I could follow step A to step B to step C. On the other hand, he says, I can safely say that nobody understands quantum mechanics. He wrote this in 1940. It still applies today. It still applies today, almost 100 years since people invented it. It's, I was, in Office Star today, I was saying like that, one of the things that's so hard about quantum mechanics is that what you find here is that we don't even have the language to talk about things. Like if you're talking about Newtonian physics, you could say, oh yeah, here's a ball, we could bounce it, we could throw it off the wall, and yeah, we could take the card, we could squish it down to a particle and draw a free body diagram and go like, yeah, that's the center of mass. But when you get to quantum mechanics, I can't take a little ball and say this is an electron. Even though we draw it that way, the Rutherford and Bohr model does that. But quantum mechanics comes back and just says, that's a bunch of bullshit. That's not the way it happens. And you're going to see that I don't have the language to explain to you what is an electron, what is a proton. And when we get to the photon's an animal that, wow. In 4C, when I would teach the full class of 4C, I would tell students you cannot say the word photon before you know what the hell you're talking about. And then when people finally saw what the photon was and they started, seeing me describe it like through like Feynman's book QED, most people would, some people would say to me like, you see, I don't like the photon anymore. I like the light wave. And I go like, oh yeah, me too. But the problem is that we're gonna have a failure in language. And I don't know how to tell you that. And, ultimately, what I should probably say here or start off talking about is that why did quantum mechanics arise? And the reason why quantum mechanics arose was that when you looked around the 19th century, what ended up happening is that people were starting to ask the questions about Maxwell's equations. In other words, how does light interact with matter? And so they were asking this very simple question. And it was in this interaction of light with matter that the problems all started to arise. And I cannot tell you how many people have said this in the past. They thought that at the end of the 1800s, there was a lot of people that said, oh yeah, the end of physics is here. We're going to be able to describe everything we possibly can. Well, I just want to remind you, the atom was not invented yet. It is true that there were people that believed in the atom, but there were very few. The atom did not come into existence until Albert Einstein put it on the map. And he did two very, very important calculations, one of them being that he derived Avogadro's number from a theoretical calculation. And that had never been done. And that's when a lot of people started to do that. But we're getting off topic. So what we really want to ask right now is, why did quantum mechanics arise? Okay. So let me go to this. So the question that we're asking here is that, I don't know if my pen's working. There it is. Okay. So what we're really asking is, why did quantum mechanics have to rise. So a lot of times, since we were going to write quantum mechanics a fair amount, I typically just write QM for quantum mechanics. And the answer was that at the turn of the 20th century, what they were doing here, that there was attempts to explain how radiation, in other words, electromagnetic radiation, interacted with matter. And what you're going to see here is that during this thing here, what you find here is that classical physics, right? The thing that people were saying that it was going to be the end of all physics, right? Classical physics broke down and was not able to explain experiments. That's simple. That is, there were God, how do I say this? How do I write this? God, I can't even pronounce the word in my head right now.
Irreconcilable.
Oh, yeah. Thank you. You just couldn't solve these problems no matter what. And it turns out that there was a whole series of problems. Okay, there's a whole series of problems. So there are many of these. But here is a short list. So the first one, that atoms shouldn't exist at all. So if you look at the model of the atom at this time, it shouldn't exist. It's known as the Rutherford model. And if you think that the Bohr model, for some of you that have heard the Bohr model, fixed it, it didn't fix it. Okay, the Bohr model is actually, it's a semi-classical theory. That means part of it is quantum mechanics, part of it is classical physics. So it's not even quantum mechanics. So they couldn't fix the problem of the atom. And the atom, the existence of atoms, actually were not, theoretically derived until 1927. So it wasn't a simple question to answer. Two, there was something called the blackbody radiation problem. It was called the Ultraviolet Catastrophe. And I'll talk about this one. That one's probably the hardest one conceptually to understand. It's a very subtle problem. And it's essentially, what kind of radiation do hot objects emit? It's called blackbody radiation. And then the third one here, which is the easiest to understand, is called the photoelectric effect. The fourth one is known as Compton scattering. And the fifth one is atomic spectra. So these were just a short list. By the way, there's dozens and dozens of more. But this is a short list of problems that classical physics could not understand. could not explain at all. And then came quantum physics. All of these problems were resolved by the introduction of a new constant. And that constant is known as Planck's constant. And Planck's constant goes by the symbol little h. And this number is tiny. This number is of the order of 10 to the negative 34 joule seconds. And that number being so small tells us why you don't see quantum mechanical effects in everyday situations. And if you were able to be at the scale of this number here, you would find quantum mechanics to be, it would be common sense to you. You'd go like, oh yeah, this has to happen or that has to happen. But you wouldn't be comfortable with it. But essentially, that's why quantum mechanics arose. You could not solve how radiation interacted with matter. And when classical physics tried to do that, it utterly failed. And it failed in a big way. Now, historically, the way things happened here is that it's typically the ultraviolet catastrophe started first, and then it went to the photoelectric effect, and then it went to Compton scattering, then it went to atoms shouldn't exist, and then it went to atomic spectra. So this is not historical. This was just sort of like the easiest way to actually look at this.
So I'm still not sure how come the top one, because I mean the top one sort of ties with all of them, shouldn't it? Or
Sure, it does. It does.
yeah,
But I mean, I'm just saying that if the atom could be described by classical physics, as you'll find out in, I think it's in chapter 4. In chapter 4, you're going to get a problem where you're going to get the Rutherford model or the Bohr model, whichever model you want to talk about. And you're going to see that if you really had a model like that, an electron circulating around a solar nucleus would radiate so much energy that it would crash in 10 to the negative 8 seconds. So an atom would only exist 10 to the negative 8 seconds. And you have a homework problem where I'm asking you to calculate that so that you could see that according to this model of classical physics, atoms shouldn't exist. So, but ultimately, it's this Planck's constant that answers this question again and again and again. And the only way to get to this is that we essentially have to get to what's going on. What's this, atomic behavior that's going on? So what do I propose? So in lecture 3, what you're going to see here is that in this lecture, it's actually the quantization of energy. And light. That's the title of it. And I think that's a really, really good title. And what you're finding here is that it actually started with Planck. He was sort of like the reluctant scientist, as some people call him. And you're going to see that the way I'm going to order my lecture here is that I want to start off with blackbody radiation. and the ultraviolet catastrophe. And when you look at this ultraviolet catastrophe, you're going to see that classical physics predicts something that's quite crazy. And luckily for us, we don't have a classical world because we'd be bathed in, X-rays and gamma rays, and we'd all be dead. We'd be radiated to death. And then what we'll start then here is that then we're going to go to the photoelectric effect. But I want to say here that this is a very subtle problem. Okay, this is the black body radiation problems. It's very challenging conceptually, and I'll do my best to help you out in it. But it really requires a lot of physics thinking, not only in this class, but in other classes that you've had. So you'll be challenged on this one. This one by far is the easiest to understand, the photoelectric effect. It's the easiest one to see why classical physics failed. And then what we want to do is that we want to go on to Compton scattering. Compton scatterings are really out there. There's some of the mathematics of Compton scattering are quite challenging, but conceptually, it's just bizarre. Man, you go like, what? Are you kidding me? And it really, I think Compton scattering, I think what it really does here is it starts to blur the meaning between a wave versus a particle. And you're going to see that that's going to become a problem, especially as we get later on in the course. Because, as we move to the quantum model, there's going to be a battle between these two pictures right here. And I'm going to try to tell you, don't go down that dark alley. If you go down that dark alley, you're not going to be able to turn around. Nature is nature. And you're going to find that nature is not particle-like. It's not wave-like. It's not black and white. It's more complicated than that. And textbooks and online courses, they'll keep going like, well, sometimes it's a wave, sometimes it's a particle. I think that's a bunch of hogwash. It is what it is, period. And what we got to do is that we have to realize that quantum mechanics says that we have this thing that's a wave packet or a quantum particle, which I prefer to call it, and it has its own characteristics. And so that's where I really want to go. So I'm going to start with black body radiation. A lot of people don't like to cover it, but the physics is so good that it sets you up for the future in thinking in this way. And that's why I want to look at that. So here we go. The first thing I want to cover here is that I want to do black body radiation. So I'm going to come at black body radiation in a way that's quite different than what almost all textbooks. And what you find here is that, what do I mean by black body radiation? So the first thing that I should do here is that I want to come from a very physical viewpoint first. And so imagine the following thing. So suppose you heat up a solid object. Okay? You want to heat up a solid object. Now, it would be really, really beautiful if we could literally be in the classroom and I would demo this for you. But guess what? We're not in the classroom. And I actually looked for damn videos to actually kind of try to do this, and I was unable to find any videos that would do this. Now, I'm sure they're out there. I just didn't find them myself here. And so what happens here is that as you heat up an object, it emits radiation. I should be careful. Electromagnetic radiation. Now, one of the things that you have in, so when I'm thinking about a solid object, so if I say a solid object, probably the easiest one to think about is a solid metal. And when I'm thinking about this, I'm sort of like thinking, you could imagine that I have maybe a hot plate, right? So if you have a hot plate, you could imagine that that hot plate is sort of like something like this. And an old school hot plate has this sort of like iron rod that carries electrical current. So as you run current through this hot plate, it gives off radiation. And so one of the things that you find here, and I mean, for right now, that if this thing was to get really hot, so if enough current flows through it, it produces a continuous spectrum. And what do I mean by a continuous spectrum? Well, I mean something like this here, right? I look at the visible spectrum and I say, yeah, it's going to look something like this here. And so what I mean here is that, so if I was to kind of explain, why do I get a continuous spectrum? Well, what we know here is that, so why a continuous spectrum? Well, I could give you a cheap answer, and would be my cheap answer. And my cheap answer would be something like this here, is that we know that metals have many electrons. And it's the electrons, excited electrons, as they get accelerated, they emit radiation. That's the classical picture here. And so what you're seeing here is that, so metals have many electrons, and when you get, I don't know how to say this, is it maybe jostling of electrons? When you get the jostling of electrons, what you find here is that you sort of get a, how do I say this? You get a smearing out of the details. And so this language here is really bad because I don't know how to say it. Because what happens here is that I already know the quantum mechanical picture. And in quantum mechanics, you get discrete lines. But when you're dealing with a lot of electrons, you go through a process called decomposition, which means that you can't see the atomicness of particles anymore. And so what I'm saying here is that you have these metal electrons, you run current to them, and you're exciting them in random ways. And so these electrons, I imagine, are all shaking at different frequencies because of the way the metal works. And so you smear out the details. So as you smear out the details, you get a continuous emission of light colors. So I would call this very crude explanation. Okay, it's a very crude explanation, but I think it's the best for what we're dealing with right now. So when I look at this hot plate, and if I plug it in and I want to put the heat, so I want to set it to the lowest setting. So now what I'm going to do here is that light from a hot plate or from a filament is then going to give you the spectrum right here. You would go down this spectrum line here. So here we go. So what you find here is that now we want to imagine a little demonstration. So imagine this demonstration. So the first thing that I want to do is that I want to run the lowest electrical current through the hot plate. Now, you already know that if you put it in the lowest setting, you probably know that if you put your hand right above it, you can't see light coming from the hot plate, but you can feel it with your hands. So what this implies here is that at the lowest setting, you can't see visible light, but you feel infrared light, right? So so-called heat waves reaching your hand. Okay? Reaching your hand. And so I would say that right around this edge right here, I mean, you're really seeing, it's outside of the visible spectrum, but infrared is right here. You can't see in the infrared. So you're outside the visible spectrum. But then something really interesting happens. What I would do now is that now I would run current. I would run a higher current now. So if I run a higher current, what you'll see here is that the light changes now. As I run more energy through that, what you start to see here is that it starts to move in this direction. The hot plate gets what? More reddish orange. So what you're finding here is that you run a higher current, the hot plate gets hotter and it becomes more red orange. And what you find here is that the hot plate can't really work with this. And what I would do now is that I would switch to a light bulb. So now I switch to a light bulb filament. And what you're going to see in the light bulb filament, let's say that this is my light bulb. And you typically have sort of like a wire that kind of can do something like this here. And what you find here is that if I now increase current even more so, you're going to see that what ends up happening is that the sky starts to really get more yellow. It goes from, so as you can see the spectrum, it's going from this orange and red, and it can reach this yellow region here. And what you find here is that even more so, you can get a yellow light that is much brighter and hotter. And so what you're finding here is that the question is, what that you so in summary,
How come it never turns green?
you can, but you gotta get it higher than 5,000 degrees. And that takes a very special metal, because if you take regular filaments at, when they get to the temperature of the sun, it's right. If light bulbs are about temperatures of the surface of the sun, about 5,000. So when you get above that, most metals start to melt, and you get the bulb that actually, the filament will just vaporize. So you
So if
have
it was
to.
a tungsten filament, it would theoretically be able to be green, or would it need to be even more like dense than tungsten?
I think tungsten. I think the melting point of tungsten is like 5,600 K.
Right, but I think the issue here is we're seeing the superposition of all the frequencies of visible light below green on top of the green, and so what we actually see is white. So it goes red and then yellow, and then
Oh no. Oh, yeah, as you go to, I agree. I see. Okay, now that's a much more complicated question. I wasn't trying to get that complicated. But what ends up happening is that you're right. You do get a superpositions of many colors, but we're talking about the peak of the curve. When are you going to get the max? And you have to go above. You have to get to essentially the temperature of the sun to get the green. So if you could get a metal that you could heat up to get to the temperature of the sun, then you would get the green color. Right? But that means it has to be the dominant. And when we look at the black body radiation curve, you'll see what I mean. I mean, what color is the sun? I mean, is it yellow or is it white? So if you were in outer space, what color would you see compared to if you see here on Earth? Yeah, that's
sort of a meaningless question also, because our range of light reception is designed evolutionarily to be to focus around the maximum emission of the sun at Earth's orbit.
That is exactly right.
The visible spectrum.
That is exactly right. But I guess the question is that if the atmosphere was gone, would the sun color be any different? And the answer is yes.
Well, in California right now.
But anyways, in summary, what I'm saying here is that two things happen. One is that so higher currents produce brighter, more intense light. So the intensity of the light gets higher. And the other thing here is that there's a shift in color of the light. And one of the things that, what I mean by that is that if you look at this, we started off at black at the infrared region, and then we started to move closer and closer and closer, and we're shifting in that direction. So the black body radiation, or the heat, the radiation emitted from this thing is doing that. So if I was to actually look at a curve of sort of like the radiation intensity, it seems like it's doing something like this. So I start off at this very dark red, and then as I get more and more towards, I don't know, can we get orange? We get more and more towards orange, it gets actually brighter. And as we get more and more closer to yellow, it gets, brighter and brighter. And as if I get more and more, if I was to go all the way to green, which we can do, you would see that there's this trend where the color is shifting and things are starting to get brighter. And so what we want to do here is that then we want to ask the question, right? So by the way, I'm judging this by frequency, okay? And one of the things that I want to do here is that that's exactly what you see when you look at a black body curve. Okay. And so let me go share my screen with you so you can see what I'm talking about. So if you look at this black body curve, what you're finding here is that, look at the temperature. This is the temperature of a light bulb. Okay. And then the temperature of the sun is here. So when you're looking at that, you can see that as I now run more, so if I take a bulb, most of the peak light is in the infrared. I really hate that this is in wavelength, but it is what it is. Nothing we can do about it. And what you're finding here is that as I increase the current, okay, as I increase the current through that, the temperature, which is around 3000 K, is now going to start to go up. And what you're seeing here is that there's a shift in the peak. So that means instead of emitting more infrared light, it's now peaking almost in the red visible light. And if I continue to peak, you could see as I increase the temperature, you get more red coming out, but that doesn't mean that you're not getting all of the other lights. And what you're finding here is that I start to decrease the amplitude because I won't reach it. If I continue to go up, you could see that as I go to higher and higher temperatures, the scale gets more and more. Let me increase this a little bit. So you could see around the temperature of the sun, I'm a little above it, I believe. It's peaking in the lime green, like Jason was talking about. And this is where evolutionary wise, here's where we see the best light right here. But if I continue to go, you could see that hotter and hotter temperatures is producing more and more intensity, and it's shifting all the way to the left. So the question that we got to ask is this: what does classical physics say about this curve? And this was the first hint that classical physics cannot explain the interaction between radiation and materials.